The Goldbach Variations, 23 trichordal variations on Goldbach's conjecture, for piano.
Introduction. The philosophy. The German mathematician Christian Goldbach was born about 5 years later than Johann Sebastian Bach, and he also died about 5 years later. Today, Goldbach is particularly known because of his Goldbach conjecture. Goldbach's conjecture states:
Every even number bigger than 2 can be written as the sum of 2 primes.
Goldbach's marginal conjecture states:
Every odd number bigger than 5 can be written as the sum of 3 primes.
Obviously, the original conjecture implies the marginal one, but not the other way around. A Goldbach partition is the representation of an even number as the sum of 2 primes. For example, 3 plus 5 is a Goldbach partition of 8. For the present Goldbach variations, the reliability of the conjecture is of no importance. Instead, the variations are built on the asymmetries implied by the partition of numbers into possibly different primes. Western music, with its developing music theory, the theory of form, the different time signatures, and its phraseology, are always based on symmetric partitions.
In music, not numbers but durations are divided and subdivided all the time. This is to say, the values of notes are mostly measured in halves, fourths, eighths, sixteenths and so on. Expositions typically count 4, 8 or 16 bars, all of the same length, and the typical form of a piece is also very symmetrical. A-A-B-A, A-A-B-B and so on.
If you partitioned numbers in the traditional manner of Western music history, you'd typically partition 8 in 4 plus 4, 12 in 6 plus 6, 16 in 8 plus 8, and much less frequently in 3 plus 5, 5 plus 7 or 5 plus 11. The present Goldbach variations are the attempt to oppose this traditional tendency of symmetric partitions of durations. There are 23 variations, which length corresponds to the 23 first primes. The varied theme is no particular melody or harmony, but the partition of all occurring durations or numbers in possibly different primes, which then are subdivided again in more primes, and so on.
With regard to the harmony, I use different types of trichordal hexachords, namely always a new hexachord for each bar. If a piece is made of different sections, of course a prime number of sections, so their lengths behave in relation to primes, and wherever a longer part is subdivided in more shorter ones, the ratio of the latter is always correspondent to further different primes. Moreover, if equal values follow each other, their number will always be a prime.
However, between music and number theory, there is a substantial inherent difference. The basic unit of the natural numbers is 1. 2, therefore, is clearly the smallest prime. In music, there is no basic unit, because even the shortest duration or note can always be subdivided in even shorter notes. An eighth note, for instance, can be prime in the same manner as a whole note or as a 32nd note.
Therefore, the unit in which I can count can be modified arbitrarily. Thus, in music, there are always many more possibilities for a Goldbach partition than in number theory. I'll give you an example. The number 24 can be partitioned in 5 plus 19, 7 plus 17 or 11 plus 13. A half note corresponds to 24 32 notes under triplets. Therefore, the mentioned partitions can be applied as well. Furthermore, this half note could be subdivided in 3 plus 5 16th notes. 5 plus 11, 32 notes, 3 plus 29, 64 notes, or in 3 plus 7, 16th notes under quintuplets.
Theoretically, there is always an infinite amount of possible partitions, even if they always get more complex and less feasible in performance.
Accordingly, I could also subdivide my half note of the example in 3 plus 1/8, or 2 quarters, since the eighth could be represented as the unification of 2 16ths, 2 being a prime 2. To divide the half in 2 quarter notes is allowed for the same reason as I can write 3 or 5 or 7 quarters, 8th or 16th notes consecutively.
So, the Goldbach variations are thus concerned with a prime number mentality applied to music. Along these lines, it is more appropriate to speak of Goldbach variations rather than of Goldbach partitions. Most of the structure of the Goldbach variations is based on primes, but there appear a few exceptions.
For 8 of the 23 primes, also the 88 keys of the piano have been partitioned into the 4 primes 17, 19, 23 and 29. It is striking that neither 8 nor 4 are primes. The division of the 88 piano keys in 3 or 5 primes is of course possible. For example, 2 plus 19 plus 67, or 2 plus 13 plus 19 plus 23 plus 31. But musically not very satisfying. I wouldn't enjoy composing for one of the 23 pieces by only disposing of 2 piano keys.
Each of the 23 pieces is assigned a different prime of the first 23 primes, and those primes determine the length of each piece, measured in dotted whole notes. Now, while writing music, one can distinguish between length and duration of notes.
A quarter note with metronome 60, for example, lasts the same amount of time as a half note with the metronome 120 for each quarter. By either choosing between an equal metronome for all pieces, which would provide the exact proportion between them as their assigned primes suggests, or different metronome numbers, which assign different durations to the same note values of different pieces, I opted for the latter, even though, in this way, different pieces can have the same duration.
In fact, if a piece with its total length of, for instance, 61 dotted whole notes was assigned the metronome number 61 for each fourth, and if another piece with its total length of, for instance, 43 dotted whole notes was assigned a metronome of 43 for each fourth, then consequently both pieces have the same length, even though by comparing their fourths they have the wonderfully asymmetrical ratio of 43 to 61. On the other hand, and sadly enough, both pieces will last exactly 6 minutes, or 360 seconds, both clearly no prime numbers. What a pity. The structure. The Goldbach variations consist of 23 pieces for piano solo of different lengths according to the first 23 primes, which are distributed in this manner.
Here, the piece in the middle, measured in note values, is the longest, lasting 83 units of dotted whole notes. The shortest is piece number 9, with a length of 2 dotted whole notes.
Those primes have also been chosen as the name of the pieces, and at the same time their metronomic number. However, the composer decides which unit is meant by the metronomic number. The pitches of all pieces are determined by trichordal hexachords.
Type N, normal hexachords, are made of 2 normal whole tone trichords connected by a half-tone step. Type Z hexachords are made of 2 normal whole tone trichords connected by a half-tone step backwards. Type Z hexachords are made of 2 normal whole tone trichords connected by 3 half-tone step backwards. The same hexachord can also be seen as 2 diminished trichords connected by a half-tone step. Type T minor third hexachords are made of two augmented trichords connected by a half-tone step backwards. Type H half-tone hexachords are made of two diminished trichords in a distance of 3 half-tone steps. Type H stroke narrow half-tone hexachords are made of two diminished trichords connected by 2 half-tone steps.
5 different types or forms of structure called A, B, C, D, and E are assigned to the 23 pieces of the Goldbach variations in this manner. The middle piece, number 12, is the only one using the type A. Being in the middle, it divides the Goldbach variations in 2 parts, which will further be subdivided by the pieces of type B, namely 6, 16, and 20, in 2 and respectively 3 smaller parts. The 5 remaining gaps of 2 times 5 and 3 times 3 now will always be divided by pieces of type C, number 3, 9, 14, 18 and 22. Here are the type E pieces, and finally the remaining pieces of type D.
Musically, only the type A piece uses Z hexachords. The pieces of type B use N hexachords. The pieces of type C are using D hexachords. The 4 pieces of type E use double Z hexachords. Of the remaining 10 pieces of type D, the number 2, 4, 8, 13, 15, 17 and 23 use H hexachords, whereas number 21 uses double Z hexachords, and finally number 10 and 19 both use narrow H-stroke hexachords.
So there are 5 pieces with double Z hexachords, 4 of type E and 1 of type D, 7 with normal H hexachords, and 2 with a narrow H-stroke hexachords, 5, 7 and 2 being obviously primes.
Now the first 23 primes are distributed again, but differently, over the 23 pieces. We can observe that pieces of type E aren't assigned any new primes. Later I will explain what their purpose is, but first I would like to say some more general things about the 5 types.
The pieces of type A, D and E do have a prime number of bars. This is not true for pieces of type B and C in order to break this symmetry. In any piece the hexachords change with the bars.
Each bar has his own hexachord.
In order to break the symmetry, as any symmetry shall be broken, this rule, which is very symmetrical, does obviously always hold.